In our unit thus far, we have strictly used trigonometry to solve angles and sides of right-angled triangles. But it is possible to use trigonometry on triangles that aren't right-angled triangles as well. And that's what we're going to look at today. So we're going to look at how we can use something called the sine law and the cosine law to solve for missing sides or missing angles on triangles that do not have a 90-degree angle. The first thing that we're going to go through though is how do we know when we can use any of these specific types of trigonometry. So the three different types of trigonometry we've learned before. The first is our three trig ratios, sine, cosine, and tangent, or using SOHCAHTOA. We use this strictly when we have a right angle triangle. So you can see on the right here that I have a right angle triangle, I have an angle that I'm working with 55 degrees, and I'm given another side, and I'm looking for side D. So anytime we have a right angle triangle, we want to use the three trig ratios or use SOHCAHTOA to solve for the missing side or missing angle. But what happens when I don't have a right angle triangle? So there's a few different situations that can occur. The first one we're going to look at is this triangle down here. Notice how this triangle we have an angle that's 38 degrees, a side that's 7.1, and another side that's 4.5, and we're looking for an angle theta. I don't have a 90-degree angle, so I can't use my trig ratios, and realistically I wouldn't be able to label my sides. I don't have a hypotenuse, because a hypotenuse only exists on right angle triangles. Because of that, I wouldn't be able to figure out which side is adjacent or any of the other sides related to this angle. So we can't use SOHCAHTOA. So when I'm given an angle such as this 38 degrees right here, and I'm also given a side that is across from that angle, so this 4.5 millimeters, we say that those two things are a corresponding angle-side pair. And specifically, we've been given a corresponding angle-side pair. And when we have an angle and its corresponding side given to us in a triangle, we can use the sine law. So the sine law here states that the sine of any angle in our triangle A over the side length A, and remember that an angle always corresponds to the side directly across from it. So the sine of any angle over its side is equal to the sine of a different angle in the triangle divided by its corresponding side, which is also equal to the same ratio as the third angle divided by its corresponding side. So if I have one of these corresponding side angle pairs, such as 38 and 4.5, I can use sine law because I can completely fill out one of these ratios. So for this example, we could say that I have the sine of angle A, where angle A is 38 degrees, over side A, which is 4.5. So whatever this ends up equaling when you divide those things, that ratio is the same as saying the angle of sine of angle B divided by side B. So you could see that we could use that ratio to figure out what theta needs to be. Because I know that the sine of whatever angle theta happens to be divided by 7.1. Those things have to equal. In this example, I don't even need this third ratio. And in fact, anytime we use the sine law, we'll only be using two ratios at any given time. But see how I have three things given to me. I have an angle, I have a side, and I have a third side or a second side. And now I'm just looking for a missing angle. Now we can only use sine law if I am given an angle and side corresponding pair. If I'm not given an angle side corresponding pair, then I'm going to move down to these two examples down here. Let's look at this first one. I'm still given two sides, 13.2 and 15.9, and an angle 106.4 degrees. But notice how none of these sides have an angle across from it given to me. So 13.2, I don't have an angle down in this bottom corner. 15.9, I don't have an angle in this corner. And 106.4 is an angle, but I don't have its corresponding side. So even though I'm given three different things, I don't have an angle side corresponding pair. Well, if this is the case, then we can use the cosine law. So the cosine law states that for a side c, let's say, or in our example it would be x. So x squared or c squared equals a squared plus b squared, or the other two sides squared, minus 2 times side A times side B, and then times the cosine of angle C. Now, it's important to realize that whatever side here, which is side C, this is a corresponding side to the angle that we're taking the cosine of. Those two things are corresponding always. So if you're given side C in the question, then you're probably going to be looking for side or angle C. But it's important that those two things are corresponding. One easy way to recognize that we're going to use the cosine law in a triangle is to look for what I call a side, angle, side sandwich. Or, in other words, an angle that's being sandwiched between two sides. So in this case, 106.4 is being sandwiched between the sides 13.2 and 15.9. So if you see a side, angle, side sandwich in your triangle, chances are, or good chances are, that you're going to be using cosine law in the question. There is one other case that we could use cosine law, and that's if we're given a side, another side, and then even a third side, but no given angles. We can't use sine law for this because I'm not given an angle with a corresponding side, but I am given three sides. So if you look at the cosine law itself, I can fill in side A, side B, and side C to where C, A, and B go, and I can fill in those as well. And then I just solve or look for what angle C happens to be. And for this example down here, because beta, which is the angle that I'm looking for, is across from 12, the 12 side has to be the C side in the formula because it corresponds to the angle that I'm looking with. Example number 1. Wacko, Yakko, and Dot are standing on a soccer field. Yakko is 23 meters from Wacko. From Wacko's point of view, the others are separated by an angle of 72 degrees. From Yakko's point of view, the others are separated by an angle of 55 degrees. This is a tongue twister already. So, two things we want to do. First of all, we want to sketch a diagram to represent the situation. And then we want to determine the distance from Yakko to Dot to the nearest tenth of a meter. So it's important that we properly sketch a diagram like this. So what I'm going to do is I'm going to highlight some important pieces of information, and then hopefully that'll help us when we want to draw a diagram. So first of all, Wacko, Yakko, and Dot are standing on a soccer field. Okay, that's great, but I don't really need to highlight anything there. Yakko is 23 meters from Yakko. Okay, that's important information right there. And so what I can do is I can just draw a line or something. I don't really know what this triangle is going to look like yet. We'll probably use Y to represent Yakko and W to represent Wacko. So it says Yakko is 23 meters from Wacko. So let's put Yakko right here, and we'll put Wacko right here. And we'll put a line between them. So we're probably going to be making some sort of triangle here. And I know that they're going to be 23 meters apart. Perfect. What's next? From Wacko's point of view, so from W, the others are separated by an angle of 72 degrees. So I have to put Dot somewhere, so let's just put Dot up here. And it looks as though from Wacko's point of view, these two are separated by 72 degrees. So you have to be standing where he is, and we say that they are separated by 72 degrees. And I guess, yeah, we could highlight that as another piece of information here. Okay. From Yakko's point of view, the others are separated by an angle of 55 degrees. Okay, so we're going to stand by Yakko here, and we're going to separate them by 55 degrees. So I'm going to have to draw another line here. Oops. There we go. So standing at Yakko, I can separate these two by 55 degrees. Awesome. So what's our question here? So this is our sketch diagram. Perfect. So question B says determine the distance from Yakko to dot, or from Y to D. So that's what we're going to be looking for. So let's throw a big X on there. That's what I want. And to the nearest tenth. Okay, so the first thing that I notice is I don't have a right angle here, so I can't use SOHCAHTOA. So now I have to determine whether or not I want to use sine law or cosine law. So if I want to use sine law, I have to have a side angle corresponding pair. If I want to use cosine law, I either have to have all three sides or a side angle side sandwich. Looking at my triangle, I currently don't have a side corresponding with an angle. This is the only side I have, and I don't have an angle for angle D here yet, so I can't use that. I don't have a side angle side sandwich. This is my only side. Even though I'm looking for this side right here, I can't, this doesn't count as a side angle side. I have to have all three of those given to me. And I don't have all three sides. So what am I to do? Well, here's a big hint. Anytime you have two angles in a triangle, you immediately want to try to find the third one, because that'll help you out. And normally when a question gives you two angles, you're probably going to have to use the third angle somewhere in your question. So remembering that a triangle has 180 total degrees, we're going to figure out this third angle D, 180, subtracting the other two, so 55 and 72. So 55 plus 72 is 127. So 180 minus 127, well, we've got 53 degrees. So that's what D is going to be, 53 degrees. Okay, now what do we have? Well, now that I have this angle and a side, I have a side angle corresponding pair. So I can use sine law. So let's write out sine law here. So I know that sine A over side A is equal to sine B over side B. And you don't have to write the third one because we normally only use two ratios at any given time. So I normally fill in the ones that I know first. So I know angle 53 corresponds with side 23. So I'm going to say sine of 53 degrees divided by 23 meters. Well, that's going to equal, and because I'm looking for side x, then I have to use its corresponding angle in the sine ratio. So 72 degrees is the angle, so sine of 72 divided by side x. I have a fraction equaling a fraction, so in order to get rid of those, we cross multiply. So I'm going to cross multiply these things. So sine 53 times x, there's a little bit of notation that we're going to look out for here. And it's important that when I write sine 53 times x, I write the x in front of the sine 53. This works the same if I'm multiplying a trig function by a number or a variable or whatever. Always write the variable or number out in front, because otherwise it looks like I'm saying take the sine of 53x, which is not what I want. I don't want to take the sine of 53x. I want to take the sine of 53 and then multiply it to x. So the proper notation in math when you have a variable or a number being multiplied by a trig function is to put that letter out in front. So that's how I want you to write it, and it's sort of the expectation. So let's get rid of this. Okay, so we cross multiply here. X times sine 53 was x sine 53 equals, and so I'm going to have 23 times sine 72. So again, put the number out in front, and we say 23 sine 72. Now we want to isolate for x because I want x to be by itself. I want to solve for it. So I have to divide away this sine 53. So let's divide both sides by sine 53. Remember, sine 53 is just some decimal number. It's a ratio, so I can do that. So these cancel. So I'm left with x is equal to, and now let's get out our calculator and we'll figure out what this whole mess is right here. Okay, so 23 sine 72 divided by sine 53. So 23 sine 72 divided by sine 53. We get 27.389 and so on. I need to round to the nearest tenth, it says, so 27.4. meters. There we go. So, therefore, Yakko is 27.4 meters from dot. Approximately. Don't forget that dot. Example 2. Find the measure of theta to the nearest degree. So we have a diagram here. Looks like we have two triangles. One triangle has a side 7.9, another side 9.5, and an angle 101.1. This other triangle has a side 12.3, another side 9.8, and an angle that we're looking for, which is theta. Again, I'm not given any right angles here, and I can't assume that I have any, so I cannot use SOHCAHTOA. Don't even think for 1 second that you can use SOHCAHTOA for a question without a right angle. So we have to use sine law or cosine law. Now I'm looking for theta here, so eventually I'm going to have to use this triangle, but if a question gives you two triangles, you can pretty well bet that you're going to need to do something on the first triangle first in order to help you with the second triangle. So let's look at this first triangle here and we'll see if, what we can do. I have a side, I have another side, and I have an angle, and look, this creates a side angle side sandwich, which pretty much means we can use cosine law to solve for the side across from the angle. So I would be able to solve for this side right here, call that x. And what happens if I have this side x? Could I use that in this triangle? Well, once I know x, then I'll have this side, and this side, three different sides on a triangle, which means I can use cosine law again to solve for theta. So this is going to be a two-step problem. We're going to have to solve for x first, and then use x to help us find theta. So let's do a solve for x first. So I have a side angle side sandwich. We're going to use cosine law, so let me write out cosine law first. So c squared equals a squared plus b squared minus 2 times a times b times the cosine of c. You will need to memorize this, but you'll use it enough that it shouldn't be a problem. Okay, now it's very important to put which side goes in the proper letters. Because c is the angle that we're looking for or that we're given. In this example, it's 101.1. The side that corresponds to that angle has to go where the c goes here. So in this case, that's our x, because that corresponds to that 101. It's across from it. So we're going to put our x squared where c is. The other two sides are a and b. Doesn't matter which order they go in, because we're adding them no matter what. So 7.9 squared plus 9.5 squared minus 2 times 7.9, put these in brackets, 9.5 times the cosine of 101.1. Now it's going to be very important that we understand BEDMAS here and we make sure that we use it properly. A big common mistake that I see is that people will solve for 7.9 squared and then they'll solve for 9.5 squared. And then they'll take that and they'll add it to that, and then they'll subtract 2. But this 2 is currently being multiplied to these three other things, 7.9, 9.5, and cosine 101.1. So if you took this and subtracted 2, you would be breaking the bedmass rules, and your answer will be wrong. So make sure that you do this properly. Now, luckily for me, or for you as well, you could probably throw it all into a calculator and it'll bedmass itself out for you. So let's do that. Let's bring our calculator over here, and we will solve for x squared just by throwing everything in. So 7.9 squared plus 9.5 squared minus, and now 2 times 7.9 times 9.5 times the cosine of 101.1. And so we get this giant number, 181.5575472. This isn't my final answer, so I'm going to want to keep as many of these decimal places as possible. So x squared is equal to 181.5575.472. So now when I figure out what x is, don't forget this isn't your final answer, and it should seem reasonable. All my other sides were, really small numbers. 181 would not be reasonable. So make sure you take the square root of this number. So we're going to take the square root of my answer here. My graphing calculator, I have an answer button. So it keeps all the decimal places for me. We get 13.474. Now again, I'm going to be using this x again in my next example. So I want to keep as many decimal places as possible. I don't want to round yet. So let's say x is going to equal approximately, I'm going to keep 4 decimal places, 13.4743. Okay. So now I know what x is equal to, so I have a side here, 13.4743, another side 12.3, and another side 9.8. How do we use cosine law again to help solve for theta? So I'll do the next example in blue so we can see the difference. Again, I have a side angle side sandwich, but in this case I don't have the angle. I have its corresponding side already. So when I write out cosine law again, c squared equals a squared plus b squared minus 2ab cos c. The angle that I am given, or I'm looking for, sorry, has to correspond to its side across for it. So the 13.4743 has to be the c again, because it's across from the angle we're looking for. So 13.4743 all squared equals a squared. Again, these sides don't matter. So 12.3 squared plus 9.8 squared minus 2 times 12.3 times 9.8 times the cosine of theta. We don't know what theta is, so we're going to keep it as theta. Now here's where things get a little bit tricky when we do the math. I can't just plug all this stuff into my calculator because my unknown is on the same side as some of my calculations. So basically I have to sort of rearrange and move things around. When we're isolating for this cosine theta, I need to get rid of 12.3 squared, a 9.8 squared, and a negative 2 times 12.3 times 9.8. That's currently multiplying with the cosine theta. So in order to properly isolate, we move things over to the other side, but think of it like backwards bedmass. You do things in reverse order. So I get rid of the additions here first. So I can take this 13.4743, I'll just keep it written right now, 4743 all squared. I'm going to move the 12.3 squared over, so it's going to subtract. going to move the 9.8 squared over, so it will also subtract. And so I'm left with this 2 times 12.3 times 9.8 times cos theta. And I mean, one thing we can do right now is just to multiply to see what those equal. So 2 times 12.3 times 9.8. So negative 241.08, because it was subtracting. So negative 241.08 cos theta. So to get cos theta by itself, I have to divide away this negative 241.08. So let's figure out what all this mess is over here on the left-hand side, and then we'll divide it by negative 241.08. So 13.4743 all squared minus 12.3 all squared minus 9.8 all squared. We get negative 65.773 and so on. Then we're going to take that answer and we want to divide it by this negative 241.08. Oops, I don't think that'll work actually. Let's divided by negative, there we go, that's better, 241.08. And so we get 0.2728274411. Okay, so let's write that out. Cosine theta is equal to 0.272827 and so on. So there's a little dot over there because we've approximated this. So to get theta by itself, now remember you take the cos inverse of whatever's on the other side. So theta is going to equal cosine inverse of this big mess, 0.2728 and so on. And I'm going to approximate it. We're going to approximate to the nearest degree it says. So I'm going to take the cosine inverse of that answer. I'm going to keep all the decimal places there because I store this on my calculator with the answer key. And we end up with 74.167. But because I'm rounding it to one decimal place, I just have to write it as, or not even one decimal place, to the nearest degree, 74.1 stays at 74 degrees. And there we have it. Theta is equal to 74 degrees. Okay, so I'm going to leave you with this example that I want you to try at home tonight and bring it to class tomorrow. So Popeye leaves the marina and sails his boat 10 degrees west of north for 1.5 hours at 18 kilometers per hour. He then makes a starboard or right turn to a heading of 60 degrees east of north and sails for 1.2 hours at 20 kilometers per hour. At the end of that time, how far is Popeye from his starting point to the nearest kilometer, and what is the course required for him to return directly to the marina? This would be a pretty good thinking type question that you might see on a TIPS. Now, this is a little tougher of a question, so if you want to try other sine and cosine law questions that are part of your homework first, and then maybe try this later, that's no problem. But I'd be pretty impressed if you'd be able to tell me the answer to this. And I'll give you a little bit of a hint. When we talk about people sailing in directions, so this says 10 degrees west of north. When we say 10 degrees west of north, this is what I mean. So let's say the marina, and when you do use this grid down here, I would plot the marina right on the origin right here. So we'll say that this is the marina M. So when he leaves the marina and sails his boat 10 degrees west of north, first of all you have to figure out where north is. North is always pointing upwards. So if I draw my directions here, north, south, east is up to the right, and west is to the left. I always have to do never eat shredded wheat to remember, even now. So if you're going 10 degrees west of north, what that means is you start north, but you go 10 degrees west of it. So if I were to draw a line, I would start north, but then I need to head 10 degrees to the west. So it would be as if I was going in this direction, and the angle between here and here was 10 degrees. Now if he goes from here and he turns to a new spot, we have to still consider the fact that north is still straight up. So if you figure out where you want to go in the next direction, you're going to need to take that spot where he currently is, create sort of a new origin, and then figure out, well, where's 60 degrees east of north from this spot right here. So that's going to be my hint to you. If you can figure this out for me, maybe I'll give you some sort of prize in class on Monday. So if you can figure this out for me, maybe I'll give you some sort of prize in class if you show me the correct answer. Anyways, good luck with this, and we will see you in class where you have plenty of time to try some more examples of sine and cosine law, especially the word problems.
It's time for Animaniacs, and we're zany to the max. So just sit back and relax, you'll laugh for Animaniacs. Come join the Warner Brothers and the Warner Sister Dot. Just for fun we run around the Warner movie lot, and they lock us in the tower whenever we get caught. But we break loose and bend bubbles, and now you know the code. We're Animaniacs. God is cute and Yakko yaks. Like a packs away the snacks while the players raise the sacks. We're Animaniacs. The Pinky and the brain who want to rule the universe. Put letters brought together, snappy laughs with a curse. Like the shades of Mindy, but we